Good afternoon.
Good afternoon, Dr. Gonzalez. Can you hear me?
We'll be starting shortly.
Yeah, sure. You can hear me, right?
Yes, sir, we can hear you. एक बार So, good afternoon, everyone. I welcome you all for another session related to quantum communication. And today, our speaker is Professor Ashwath Babu, and he'll be taking sessions on quantum memories and quantum repeaters. So, I just want you to note that today we are going to have 3 hour sessions. So, 3 sessions on these two topics, starting from 2 p.m. Till 5 p.m. in the evening. Okay, so let me introduce him to you all. Dr. Ashwath Babu, who serves as an assistant professor at physics at the Indian Institute of Information Technology, Dharwad, Karnataka, where he has been faculty member since 2016. He earned his PhD in physics from IIT Kanpur in 2013 under the supervision of Professor Harshvardhan Vanare, focusing on nonlinear dynamic phenomenon in all optical bistable systems. He holds an MSc in physics from University of Hyderabad, where he was awarded the University Gold Medal, and a BSc from RIE Mysore. He further enriched his research through prestigious postdoctoral fellowship, first at IIT Madras as an institute postdoctoral fellow, and later at Lund University, Sweden, as a visiting postdoc fellow. Before joining IIT Dharwad, he also served briefly at NIT Calicut. His research spans quantum optics, quantum information theory, and nonlinear dynamics of optical systems. And at IIT Dharwad, he actively integrates these areas with interdisciplinary teaching and research. We are thankful to him for accepting our invitation as a speaker on the in this FDP, and I will just pass on the control to him. Thank you.
Thank you very much, Dr. Rajendra. I hope I'm right. So thanks for the kind introduction. And so just give me a minute. Let me connect my tab also. I hope, yeah. I'll just connect my tab so that I can use. Okay, wait a minute. Yeah. Can you hear me? Just give me a minute. Just
Yes, we can hear you clearly.
so there's a lot of confusion here. The confusion is with the QTs. There is two QTs going on. So
Yes, this is QT-06 on quantum communication.
yes,
So just a quick question. So participants might be asking questions through the chat window. So do you want our technical team to know the make you know the questions, or will you be able to do it on your own?
yeah, I keep checking
All
the
right.
chat messages. So
Okay, perfect.
I'll just see. Uh,
Okay, perfect.
Perfect, right? EICT Academy Day-9. Okay, this is 28. What's the matter? I think how many are there? Let's see right now. Participants, yeah, right. Why is this 28th? What time this will start? No, I'm just trying the Day-9. Cancel. Panelist password. Yeah. So I'm there. Okay. Okay, everyone. So let me share my screen. Here. Here. That screen. Yes. Right. So right. If you can see, the topics was asked for me, everyone. So there are 341 people have joined. Hope people can hear me loud and clear. So let me see the chat messages as well. Yeah. So yeah. Yes. So once again, very good afternoon to all the participants over here. So the topics I was asked to discuss or introduce is quantum memories, right? So the just a moment. Quantum memories and entanglement swapping, right? These things were asked. So mainly, so one has to understand first what is memory, right? So I'll just start doing from the memory point of view, and then go on to talk some what is this quantum repeaters are, how we can do communication with the repeaters and all those things, right? Okay. So I have PPTs actually set up. So PPTs are there already, right? So I'll first use my hand notes and I teach using the hand notes, and then I go on to do once I share the material, you people can refer the material and understand what is being discussed in the sessions. So that is how it is. We will plan in that way, right? So first of all, the way usually I myself understand, or I myself try to teach a new concept based on the concept which is we are already aware. Okay, fine. So to start there, so let's go to the first slide. Let me see what I have here. Okay, so if you can see here, we can get into the field of quantum memory based on classical memory. Okay, right? So this classical memory is something which we can take it for granted because we all doing classical communication from quite some time, right? So here, if you see in the classical memory, so the information is being stored as zeros and ones, right? So the first column, or the first column, is a property with respect to the the things which we are talking about, and the second column is the classical memory. So in the case of classical memory, information is actually stored in terms of bits, that is zeros and ones. Okay, right? And on the other way, quantum memory is together you are going to save both of them in a one memory location. In that case, it is straight away called quantum memory. Okay. So looking at the topic, right? Looking at the where the topic is placed, you people might have gone through what is quantum memory by now. Okay, so probably we will touch a little bit as a kind of a recollection. So basically, at the quantum regime, the moment you get into the quantum regime, the things like particles, if you take the smallest particle, let's say electrons or photons, right? When it comes to energy, they're going to not certainly exist in fixed form. Okay, they may go statistical in nature or a probabilistic in nature. Because of that, we will use a superposition, mathematical superposition equation to explain them. Okay, so that's why the zeros and one can be, just a minute. Okay, wait a minute. Yeah, zeros and one can be used to represent that. Okay, right? So okay. Just a minute. Looks like it's stuck. Just a minute. It looks like my move. Wait a minute. Actually, it is not exiting from the presentation. Okay, so I just want to use the Google Notes. So yeah. Oh, 1 minute. Just a minute. Okay, 1 minute. QT-06. Yeah. Okay. So, so superposition is how exactly the qubits were realized is, so if you just take, let's say, an electron, right? So the position cannot be fixed. Okay. So cannot be fixed. So it keeps, even if you make to exist at 0 degrees absolute temperature, absolutely zero temperature, even in that case, it going to possess a 0 point energy. Okay, because of that 0 point energy, what happens? It is going to exist in multiple locations. If it is going to exist in multiple locations, means it will have a statistical presence or probabilistic presence at multiple locations. Okay, so because of that, what happens? People thought, can we relate that to something statistical in nature or something mathematically relatable, which is waves. Okay, right? So they are going to associate a wave with a wavelength lambda is equal to Planck's constant divided by mass into velocity. Okay, so for tiny particle, how tiny? They are actually at the level of electrons or subatomic particles or molecules. So they are going to possess wave particle duality or wave nature. So because of that wave nature, what happens? If I have, let's say, if I have a one-dimensional box, okay, 1D box, right? If I just place an electron inside, what happens is it is going to show some kind of a statistical presence inside this box. So what is the statistical presence is, it is not going to locate in one fixed location. It is going to exist at multiple locations with probabilistic in nature. What I mean is, at this, let's say, if I just try to find a location of the electron, let's say perform some 1,000 operations and 1,000 observations on the electron and try to see where the electron is located. So what you're going to see is the probability of electron is maximum at some point, okay, and at some point it is going to be minimal. Okay, So at some point it is minimal, at some point it is maximum. Basically, it is going to show a probabilistic in nature. What I mean is this, okay, right? So let's say a one-dimensional box X location running from 0 to L. If I place an electron inside, okay, at some point, let's say L by 2, there is a maximum probabilistic presence of the electron, okay. And interestingly, at 3L by 4, okay, no, not 3L by 4, okay, so this is L by 3. Hope I'm right. No, okay, let's say this is how it is. We're not fixed, okay, right? So center, you just take center. Anything either side of that center, there is a locations where the the presence of the electron is absolutely zero, right? So the presence of electron is the presence is not there, okay, absolutely there, no electron is not there. So if such situations arise, right, so this is probabilistic. Let's say this is where it's maximum, okay, wherever there is some kind of a hills are there, there is a maximum. Elsewhere there is a change in the probability amplitude, or sorry, probability of existence of the electron. So which means, can we associate this with some kind of a wave? What is that? You just divide this entire thing into parts, let's say 3 parts. So the wave would have something like that, okay, right? I should be more careful in drawing as per this, okay, right, something like that. So there is a positive peak, there is a negative peak for the wave, right? So interestingly, if you call this is some wave, some mathematical function, psi of x, and the top one is absolute square of psi of x, okay, right? So the bottom one is wave for sure, and the top one is like an absolute square of the wave, okay. So if you call this is a probability amplitude, and the top is probability, okay. So the probability would tell me where the possible locations of the electron, right? But basically I have placed the electron inside a one-dimensional box. It is showing such a probabilistic or statistical presence that the people, the scientists or physicists thought, can we relate this probability distribution to a wave which is exactly square root of that probability distribution, okay. You see, this is a square root of the probability distribution. So, and the wavelength associated with that wave is actually a de Broglie wave, lambda d, which is Planck's constant divided by mass into velocity of that particular particle, okay. So right, so what quantum physicists thought, can we arrive some kind of a quantum memory out of it, okay, right? So how I can confine the presence of electron to exist in only 2 locations. What are those locations? So it is possible to have, okay, to have electron to confine between, let's say, x equal to some L by 4 and x equal to L by 2, okay. So these 2 locations we can confine, right, position wise, roughly speaking, to understand. And so at x, like a wave, like a presence of the electron would be, okay, let's say the probability square at this point would be saying something like 40%, and for the other case it would be, let's say, absolute square would be 60%, okay. So in that way, we are actually putting a quantum state in the Dirac notation. So this is now I'm writing a Dirac notation. Okay. Fine. In the Dirac notation, quantum state it is written some alpha 0 ket plus beta 1 ket. Okay. So here alpha square is a 40%, beta square is a 60%. Okay. And some of them actually going to be 100%. Fine. So this is how a superposition would allow an electron being existing in multiple places can allow us to create a superposition state, create a possible storage of the two numbers here. The alpha and beta are allowing to store two numbers. Okay, right? In fact, if you go for complex numbers, it can allow to four numbers. Fine. Okay. So now we are trying to understand the quantum memories. So to go there, we are trying to understand what is this qubits or the quantum state which is going to store two numbers in its place at a time. Okay, fine. So literally when I'm talking about an electron, what I mean is there is a nucleus inside an atom. There is a one orbit, valency orbit. This is the outermost orbit. So electron can jump from a one orbit to other orbit. Let's say it can jump if I supply an energy which is exactly equal to the separation between the two levels, two orbits. Okay. The issue here is if let's say the lowest level is ground 0 k, highest is 1 k. Let's take a small snapshot of that. That would be a simple notation people usually use for electron to represent in a ground state. If a photon is applied with exact energy separation matching, so the electron would jump to excited state, stays there for 1 microsecond. Okay, right? Now it can't stays there forever. What happens by the time 1 microsecond is over, it drops back, electron drops back to the ground state and emits that photon, whatever it is taken. So here it is absorption. Okay, this here it is emission. Remember, one problem here is when I supply a photon to the electron inside an atom, there is no 100% certainty that electron would absorb and goes to the excited state, which means that is also becomes a probabilistic in nature, just like we saw electron being probabilistic or statistical in nature inside a one-dimensional box. Here you can think that electron can be in one-dimensional box where ground state is lower state is in one side, higher state is another side. That's kind of a one-dimensional box. Okay, right? So because of this, what we can write, electron being in statistical in nature, electron being in superposition state between 0 and 1, that was the equation we were writing till now. Okay, right? So when you see here the comparison table which we earlier saw, in the first element is how information is stored into 0 and 1. In the case of quantum memory, it is a superposition 0 and 1. The state of nature of classical memory is deterministic, and in a quantum memory, it is probabilistic in nature. Okay, right? So there's a question somebody was asking here. Okay, is the wave unidirectional in nature or it is just for illustration? Okay, so this is for illustration. I'm just incidenting, let's say a photon means a wave is propagating in this case. And if you mean to say the waves which we are taken in this case, it is, let's say a wave is propagating in one direction. Let's say if it is ending at another one point, let's say hitting a wall, it returns, like reflects back, creates a standing wave pattern. In that case, both directions are there. Okay, right? Yeah. So during the emission process, is it laser phenomena? Yeah, no, actually, during the emission process, see, the electron gets absorbed, and say a photon gets absorbed, electron goes high, and then it jumps back after 1 microsecond. It emits that whatever energy in the same light form. So here, the process is not a laser phenomenon, because in the lasing phenomena or a laser phenomena, what we'll have is so many particles, so many electrons or so many atoms together excited, and they all de-excited or the stimulated way. They emit the photons in one synchronized fashion in coherence. That is actually a lasing process. To have a lasing process or a laser phenomena, you need to have a 3-level atomic system. What we are considering is just a 2-level atomic system. Okay, right? Fine. Now let's come back to here. The superposition would get involved here because the electrons are not certainly located to ground or excited in a given time. Okay, so because of that, so we use the equation of a superposition in a Dirac form, which is just like a two-dimensional vector equation. R is equal to xi plus yj. See, this is a superposition of unit vectors I and j with the weights of x and y. Just a Cartesian coordinate system. If we just see, if this is a r vector, it is going to have a weight of x component, going to have a y component in Cartesian coordinate system like this. Just like that, even our two-dimensional vector, a quantum state vector with the basis elements of 0 and 1 with the weights of alpha beta is going to specify superpositions. Okay, right? So now let's get back to the table. We have established that the nature of quantum state is probabilistic in nature. There is a superposition involved. Okay, and one problem here in quantum states is, let's say a system is existing in such superposition. Okay, basically what you can say, it's like a coin being tossed. So during the flight, if you see, during the flight, let's say there is a coin which is having head and tail. If it is tossed during the flight, if you see, there is head and tail, both are possible if I cast the coin. Okay, so this is a coin toss, right? So which means the coin is existing in both and head form continuously. When I try to catch, it is going to fall to one of the form, right? Okay, so very nice. Now the same analogy, if I apply here, electron being existing in the ground and in the superposition simultaneously, means it is doing a rotation between head tail. Na? So it is actually, in a way, you can say it is doing a hopping between ground and excited continuously. You can say it's some kind of a Rabi oscillations. Okay, it's called a Rabi oscillations. Okay, so now the quantumness is itself being existing statistically in two places at a time. The moment I make an observation, means make an operation on this particular system, what happens? This quantumness gets disturbed or get destroyed. Okay, so that means the quantum state, one of the probability amplitude correspond to the one of the available state, it gets nullified, and the quantum state final is going to fall onto the zero state, right? After observation, this is going to happen, which implies the observation or reading the system is actually destructing in nature. Okay, reading or observing the system, or finding to know what the system is, finding to know the status of the system, okay, forces the system to fall to a classical form, okay, right? So which means quantumness is going to be destroyed. So such thing would not happen in the classical reading, not destructive. You can do as many number of reads as you want. But remember, in quantum case, the destruction is happening means systems are very, very sensitive, and the superposition is collapsing onto a single state. Okay, even in that case, we can go around and we can utilize this to have a advantage. So we'll see that. Okay, and now coming back to the classical memory, you can copy the classical memory as much as you want. Okay, but on the other hand, I think cloning is covered to you people earlier. Okay, cloning is being covered, which means you also already know what is a cloning. So you now I agree that cloning is not possible in quantum computing or quantum qubits. Cloning is not possible. Okay, in quantum memory. Okay, so that is very, very important thing you should know, right? So again, you can go around and utilize this limitation as an advantage when it comes to quantum cryptography or quantum secured communication. Okay, so remember, wherever there are limitations coming in for a quantum computing or a quantum memory, uh, where our limitations are coming, those limitations could be turned around, made into advantages. Okay, like earlier said, destructive measurement of quantum systems leads to collapse. So in that way, okay, I can easily know somebody is fiddling with my quantum states. At the same time, let's say somebody realizes that they will make an observation, means they're destroying the system. So they cleverly they think that, okay, let's clone and try to get the information out of it. So even in that case, they're not able to clone because quantum system never allow one to clone from one to multiple quantum states. Okay, right? So that is one of the difference in classical memory quantum memory case. And if you just go to this the lifetime of quantum memory, people call it as a coherence time. In this case, it is, in the classical case, it's indefinite. As long as you want, the system can retain the information, okay, in it. Okay, but in the case of quantum, it has a lifetime. Okay, what I mean by lifetime, there is already one lifetime I have spoken. Okay, right? So let's take again, let's take this semi-classical picture of this electron in a ground state of an atom. Okay, when it jumps to the excited state by observing a photon, it stays there in the excited state, let's say 1 microsecond on an average. Okay, so that time is called a T1, 1 microsecond. It's a lifetime of the electron in the excited state. Okay, right? So by the time it is about to come down, what I can do, I can send one more photon. Let's say electron is just gone down. After 1 second, I can send a second photon. Let's say this is photon 1, this is photon 2. Okay, now I place my photon 1 and 2 in such a way that they are exactly placed 1 microsecond apart. In that case, what happens? By the time electron comes down, again it takes a second photon because it is just coming, and then electron would jump again to the excited state. Okay, so right, a photon is emitted and again photon is absorbed, again the photon is emitted. So in that way I can place the photons in my 1 microsecond apart. So how you can take multiple signals and then combine them, and you can create some kind of thing called a pulse. Okay, a pulse is created if the pulse is, let's say, pi by 2 area, pi by, okay, pi by 2 area pulse. If that kind of a pulse is there, and if that pulse goes an incident onto the electron, right? So the pulse is consisting of so many photons equally spaced in time. Because of that, what happens, if there is any electron, it gets hops between ground and excited. That is where I am going to see a superposition state of electron being in ground and excited, just like a quantum coin, analog to a regular classical coin being flipped. Okay, now I just talked about excited lifetime, which is T1, and at the same time the hopping is there, right? So how long this oscillations or hopping would exist, that is also you can specify by some quantifying time. So that is actually called a T2 lifetime, T2 time. So which means the oscillations would exist for some time. It's just like you have seen the damped oscillations. The damped oscillation means oscillations will be there after some time, just damps out because of some kind of a damping effect. Okay, right? So if you just take a simple pendulum, okay, you make an oscillations, okay, create an oscillations, it does the oscillations, after some time it dies down because you have given a maximum amplitude of certain height, some altitude you have given for a stable pendulum, and then it oscillates after time. Every time it loses this amplitude, okay, so it draws down to stable state, equilibrium state. The same way the oscillations dies down, damped oscillations. Okay, so here in the Rabi oscillations also damps down. So how long it will exist? Let's say this is some proper oscillations that exist for the lifetime of time 2, time t. So that you can call it as oscillations time. Okay, right? So I presume the system to exist in that kind of a superposition state, like depending on how long the oscillations would exist, so that you can call it as a coherence lifetime of the system. So which means it is again limited in time. So here in this case, in the table, it says lifetime is something like microseconds to few seconds. Okay, depending on the system, you can have a few seconds coherence time. These days, very long coherence time systems have been already came up with. Okay, so the question somebody was asking, uh, does damping leads to decoherence in quantum, right? Yeah, of course, that is what the main cause of the system, which is creating issues for us, right? So when I say a system is being taken in superposition condition, it is exposed to the environment. The environment actually creates such kind of a damping. Okay, so just to understand the damping, you just take the same pendulum. Okay, we do the experiment in air. Okay, if you try to do the experiment in water, okay, you see the damping happens much quicker. Okay, so inside a water, if you try to do the same experiment, okay, so what happens, the oscillations, hardly one or two oscillations make and it comes down. Okay, so when I say oscillations wise, it should be like that much. Okay, right, inside the water. So damping effect is more. So that is what the environment is causing to the system. If so many extra factors are there coming in from the environment, they may create a damping, and that may cross the loss in the coherence. So that is what the decoherence is all about. Okay, fine. So as we have seen by now, the quantum memories are going to be very sensitive to the environment. On the other side, classical memories are very robust, right? Okay, so yeah, wherever there is a limitations, let me reiterate again, you can work around, make limitations into advantage. Okay, right? So the classical memory, the primary application is data storage, and for computing you can do. Here in this case, in a quantum memory, you can use for quantum communication. Okay, and also you can create something called quantum repeaters. As we see, today we will see what is quantum repeaters as we go through this session. Okay, so some of the examples also given here: the RAM, solid state hard disk, HSD. These are the classical memories which we are in day-to-day life are coming across. Okay, so when it comes to quantum memory, there are so many various ways we can realize the quantum memories, which are called which are actually quantum atomic ensembles, nitrogen vacancy centers, and trapped ions could be a very good means to realize quantum memories. Okay, right? So yeah, somebody was asking, can you go for slideshow? So I am not going for slideshow because I just switch over to the class notes. So if I go to slideshow, I have to exit the slideshow and come. So it is causing some issue here. That's why I'm not doing. But don't worry, I am explaining everything very slow. You can go through it, my slides later as well. Okay, right. Fine. So we have established what is the quantum memory using classical memory as a base. By comparing between both of them, we got into a certain kind of understanding of what is quantum memory is all about. Okay. Now let's go a little bit more. Okay. Fine. So as per my slide, let's see how classical memories work in the first place. Okay, so maybe I can do a slideshow and then escape. That's the problem. Okay, just a minute. Yeah, it is exiting, hopefully. Yeah, fine. If you just say what is classical memory, how it will work. So basically, there would be any system which can exist in one of the other form of two states. Okay. Remember, I'm making a statement in such a way it can exist in one of the other form of two possible states of a system, which are two distinct. So people call it a bistable physical system. So the stable states can easily represented here as zeros and ones, right? Okay. So when you recollect what is bistable system, right? Most of you have gone through, okay, the bistable in the case of magnetization and all those things. Bistable systems are okay. So they are like a form of like this, okay, where the S form. So wherever there is a negative slope region is there, now this is negative slope region. Between that, this is an unstable state. Unstable state. So, right, if this is a applied magnetic field, H versus magnetization of some magnetic material. When I increase the applied magnetic field, so magnetization also increases. And after reaching the end, what happens? It switches to the upper branch. And then while decreasing the magnetization, it comes down to the top branch and it switches at the knee. They call it a knee and traces back to the old form. Basically, for a given applied magnetic field H value, let's say H naught, the system can get magnetized at a lowest value, also possible highest value. Okay, both are possible. Who is going to tell to the system whether to get magnetized at the smallest value or highest value? That is all depending on the initial condition of the system. The system initially is at a zero magnetization. In that case, the material would magnetize to the very lowest value. If it is already at the highest magnetization value, so its system is already having a magnetization. In that case, if H naught is applied, then it will drops to this corresponding value. Okay, so that is what the bistable system we see in a magnetic field. But in the case of electrostatics or electric systems, one can have such bistable system. For example, okay, energy wells, right? What are the energy wells is physical configurations where the system naturally settles into one of the two stable states. Okay, so there would be energy barrier exist between these two stable states. So between those states, system can exist in any one of the form. Okay, and remember, so just like magnetization, which we took the bistable system, here you see between the top state and the bottom state, there is a separation. This is the energy separation. Okay, right? So to go from bottom to top, you have to switch the magnetization certain value. How much magnetization you have to switch? This much value you have to switch. You have to go from very low to very high H value. Let's say H low, H high. Okay. So then the system magnetization would shift from M low to M high. Okay. So we are taking a ferromagnetic material and try to do, sorry, diamagnetic material. We are trying to do a magnetization here. That is what we see. Okay. So the same way, remember, a classical memory could be realized in this way. So the system would have a gap of some barrier. Remember that gap should not be as small as temperature, sorry, energy, like energy supplied by surrounding ambient temperature. For example, here it is given at room temperature or room ambient temperature, the amount of energy a system can take is 25 milli electron volt. So the energy gap must be more than that. Why I am saying, if I am trying to maintain the system in the like a lower energy state, the system should not jump to the higher energy state without my intervention, right? So if the temperature is around is 25 milli electron volt supplier, in that case, if the separation, the barrier which I am choosing is of the same level, then without my intervention, system would jump to the highest energy state or a lowest energy state without my control. So in that way, I lose the ability to store information with the credibility. Okay, so that is what the classical memory, the information is shared here. Okay, so let's go a little bit ahead and see how the classical memory is being realized. Okay, so here if you see, let's go, right? So electronic memory. So it's like high voltage and the low voltage of the system. So it's like charge stored on a capacitor. Okay, if you just take a capacitor, okay, right? So the capacitor can be stored to very low value and very high value. Okay, the number of accumulation of charges on each plate would create a voltage difference between two plates. Let's say initially it doesn't have any charge accumulation, so the voltage would be just 0 volt. If it sufficient the saturation of charge is taken place there, the charge of the capacitor, so voltage of the capacitor can reach to 3.3 volts. So in that case, I can treat that as high bit, and no charge, 0 bit. So this is an electronic memory created out of a chargeable capacitor. Okay, so other one is like a flash memory, right? This is solid state disk or USB. Okay, here the mechanism is electrons are allowed to tunnel through or in and out of a insulated floating gates. Okay, so a presence and absence of charge would represent 0 and 1 in this case. Okay, right? There will be a gates there. Through those gates, the charges may tunnel through or may not tunnel through. So if they tunnel through and exist at one point, we can treat it as 0, otherwise no. Okay, right? So in that way again, classical memory could be realized, right? Another one is optical memory. So these days we don't see much of this hard disks. So this compact disk. Okay, so this technology almost got obsolete. So what you see is, if you just take a compact hard disk, on the hard disk, like below this transparent region, actually using a lasers, there's a drenches some kind of a holes to a dig. Wherever there is a hole, if the light is incident, lights get reflected without any order, it goes somewhere. Where if the light, if the surface doesn't have any hole, so in that case what happens, right? In that case, what happens? The light gets properly reflected. What I mean is, the compact hard disk, let's say the surface is there. If there is a drench, hole is there. If the light is incident, it gets reflected in some haphazardous manner somewhere. Okay. But if the light is incident on a flat surface without any drench, so light is properly reflected as per the ray optics. Okay, right? So just by knowing light is reflected properly or not, we can figure it out there is the hole in this particular location or not. This is treated as 0, this is treated as 1. This is optical memory for you. Okay, right? On a compact hard disk. Right. So the another interesting way people realize the classical memory is magnetic memory. What is magnetic memory is? Let me explain. Magnetic memory. Okay. Remember, why we need to get into this classical memory is, okay, why we need to get into classical memory is, having the classical memory understood properly, we can utilize that idea to understand how quantum memory is going to be realized in the first place. Okay, right? So let's get back to the classical memory using magnetization as a means. Let's say just take a current carrying wire. Let's say there is a current carrying DC, direct current carrying wire. Okay, so that means the current, let's say, carrying from bottom to the top. So the electrons will be going from the top to bottom. So there is a current, DC current, you can say DC. So this would create a magnetization or a magnetic field around. So if the thumb would show the direction of the current, the curling finger shows the magnetic field generated. Okay, so why moving charges would create a magnetic field, which is actually explained by Maxwell, right? See, one thing for sure you can understand. What is you can understand? Let's say there is a positive charge is there. Let's say capital Q is there. Okay. If there is some another small test charge Q is there, that is also positive. Okay. Now between them there will be repulsing force. Means the electric field would create a repulsing force like that. So electric field lines always goes outside from the positive plate. Okay, right? Electric field lines. Electric field lines. They are like the some strength carriers of this particular charge Q. You just multiply that electric field strength, okay, with the small charge, test charge, okay, you are going to get what is the force exerted on that particular small charge Q. Okay, so a force Q into E is a electric force, right? Now what I'm saying is the charges themselves moves. The charges are moving. In fact, the charges moving, usually we take a positive charge as a move charge carriers, but in fact that is not. Positive charges are just going to vibrate, but actual work is done by the electrons which moves from one atom to other, and they go from all the end from top to bottom. They are actually the workhorses of this particular current conduction. Okay, fine. So the current moving charges are, they are going to have an electric field. Because of their movement, what happens? This electric field is going to change in space because of their movement. It is like, let's say, when you are just in a traffic, let's say an ambulance is coming towards you, you hear a more louder noise of the ambulance siren. When it is going away, the siren sound appears to be decreasing slowly as it recedes away from you. So here the electric field strength is going to decrease. Let's say at some point, if you just, there is a test charge, small test charge is there, the electric field due to any particular charge inside an element is going to decrease. Initially it was very straight line, okay. As it goes away and away, this field line is going to curve around. Remember, that is very important. So this straight field line going to curve around, means around, okay. I like, it's very difficult to explain. So this field line instead of straight line becomes a curve around. So electric field lines can curve around, okay. So whatever, in that case, mathematically we can write that. So actually spatially the electric field strength is varying as because of the moment. So there is a del cross E, people write, to represent the curving around change in electric field strength as time progresses or the movement progresses. This is going to create a curving or rotating magnetic field lines. Sorry, it is going to create a magnetic field lines. By nature, they are actually rotating in nature. Okay, the curved in nature. So this is what actually the electric field lines are. Okay, so this is right. So the electric field is changing in space, that is going to create the variation in magnetic field. Okay, yeah, it's going to change the variation in magnetic field, that is going to create a magnetic field lines around the wire, DC current carrying wire. So this is the Maxwell's equation, one of the Maxwell's equation. So he given whenever there is a variation in the electric field in space because of charges moving, in that case magnetic field is going to be created in that region. So remember that magnetic field could be varying in time, okay. So this is varying in time, fine. So now let me export this as well, okay. Now, so this current carrying wire creates a magnetic field around. Okay. Instead of having a line, what I'll do, I'm going to create a circle, some kind of a loop. So in this case, the magnetic field lines comes out of the center like this. Okay. So magnetic field comes out of the center, and so this is going to create some kind of a small bar magnet north and south, where here in this case field lines are like this, go exits and enters, okay, and exits and enter into the loop. So here the magnetic field lines are exiting from north, enter into the south pole. So the same way, each bar magnet is used to describe one small current carrying loop. Okay, so in the case of in the case of an atom, right, there are electrons. Let's say the valency, one electron is only there, that is going around a circular orbit or some orbit, it can be any shape. So that is going to create a small bar magnet north south. So what we can do, we can take such electron consisting atoms, let's say conductors. Inside a conductor, let's say a small conductor is there, you can arrange each current carrying loop of the orbit north south, north south, north south, okay, north south, okay. north south. On the other case, it can south north, south north. So what I'll do, this is 1 and this is 0. So this is how the classical memory is going to be created using magnetization or magnetic field alignment. Okay, magnetic field alignment on a magnetic strip. Magnetic strip. Okay, so what you can do, you can just take out your credit card. If you see behind, there is a magnetic strip which is actually consisting of the same technology of information is being created with aligning the magnetic dipole moments of each atom in a particular direction, and in the other place is arranged in opposite way. That could be another bit. Okay, so this is how classical memory is going to be realized. So now what we'll do, we'll just get into the quantum memory. Okay, let me go. All right, before taking a small break for 5 minutes, what we'll do, we'll just start what is the quantum memory is. Right here in my slide, I say a quantum memory is like a quantum hard drive. Okay, and remember, a hard drive stores the information for a very, very long time. Like we saw, quantum memory cannot be like that because it is depending on the coherence, it is depending on the Rabi oscillations, which means this information can be stored on a memory location for a very, very short duration. Okay, right? A very short duration. That is what I was telling here. And it is, by the way, it's very fragile. Okay, it's very, very delicate. Okay, so one has to, without destroying its quantum properties, one has to read or one has to use this quantum memory. Okay, all right. So this makes these things very, very crucial for building long distance communication systems and large quantum networks. So working with these fragile things is very, very important and very, very carefully one has to work. So that is what is actually asked for in the quantum computing. Okay, so we'll just quickly take a break for 5 minutes. We'll restart at 3:10 and we'll get on to see the remaining part of this discussion. Okay.